Hello everyone, welcome to my channel. In today's video, I would like to talk about one property with regard to moment generating function, which later on proved to be very useful and important. So that property, namely the uniqueness property of the moment generating function, is what I'm going to talk about in this video. Let me go through a theorem first. Suppose x and y take values in natural numbers and they have the same moment generating function. Then the probability density function of x equal to k and y equals to k for all k belongs to natural numbers. So that means the moment generating function specifies the distribution of a random variable x uniquely. To somehow simplify the manipulation and to see better what's going on, we make a substitution by z equal to Euler to the tth power. Make such a substitution. And then the original form of the moment generating function has been altered into such kind of form, gz. Okay, so now let's go through the proof of this theorem. We know that the two moment generating functions are identical to each other, and we are going to prove that pk equals to qk for all k belongs to positive integers. So we just written out the formula of the moment generating function explicitly, and since the two moment generating functions of two distributions are identical, then there is a equivalent relationship between each other. And the next step is to apply induction, mathematical induction, on n such that Pn is equal to Qn. For k is equal to 0, we see that there is just one term, that is z to the 0th power times pk, and z to the 0th power times qk. And I mean, z to the 0 is 1, then we can easily get out the result. P0 is equal to Q0. Then it comes to the second step. We assume that Pk equals to Qk for all k belongs to n up to n, from 0 up to n, sorry. Then we just remove the previous n terms and start from n plus 1 up to positive infinity. And the last step is to divide by z to the n plus 1 and written out the formula being calculated after this procedure explicitly. Why we do that is just to reduce the power of z so that it starts from power of 0, and then the else power z1, z2, and so on and so forth. We can let z tends to 0, and all the terms after Pn plus 1 has been vanished. And then we can find out the results. Pn plus 1 is equal to Q plus n plus 1. And then the original theorem has been proved. Actually, this theorem, it can extend it to random variables, not taken natural numbers. Whatever it is, it can take other kind of range of numbers or continuous random variables. But the extended theorem of this kind cannot be proved in this video because it is out of the scope of the university level math course. So, but I believe such a proof is sufficient for us to convincing ourselves that the uniqueness property of moment generating function indeed hold, and then we can apply it to various kinds of practical usages. Like for one example, chi-square distribution, it is again a important distribution later on. We can see that it is equal to the sum of n standard normal distribution square, sum of these distributions. And how can we prove that? Actually, we can just apply the theorem to compare the moment generating function of these two, the left hand side and the right hand side of the equation, and then we can see that the moment generating function of these two sides are identical to each other. And with regard to the theorem we have just proved, we can deduce that the chi-square distribution can take the form like that. Maybe I will list the detailed proof of this example in the later videos. And that's all for this quick video. Thank you very much. I shall stop here, and goodbye.